The market for optical and photonic technologies is huge, over $2.5 trillion in 2024 alone. From lasers to 3D printing, photonics is shaping almost every corner of modern life. And at the heart of so many of these technologies is one deceptively simple concept, the refractive index. By the end of this video, you'll not only know what refractive index is, but you'll see literally the microscopic processes that make light slow down in materials. Refractive index, often written as N, is a measure of how much slower light travels in a material compared to a vacuum. The equation is simple. N equals C0 over C local. But here's the surprising part. Photons aren't actually hitting the brakes like a car. Between atoms, they still move at the universal speed of light. What changes is the progress of the wavefront as a whole. To show what's really happening, let's start with this first animation. Here you can see the electric field of light moving from left to right. Watch the little dots. These represent electrons bound to atoms, like a material in glass. As the electric field oscillates, it tugs those electrons back and forth, shifting the whole electron cloud relative to the nucleus. This is called electronic polarization. It creates what is known as an induced dipole, a temporary separation of positive and negative charge inside the atom. Notice how the electrons move perfectly in step with the wave's frequency, but they're not moving far, just enough to create this temporary dipole effect. Now, here's what a single dipole actually does. This animation shows the radiation patterns around an oscillating dipole. See the donut-shaped wave? That's the electromagnetic field it emits. It's strongest forward and backwards along the dipole's axis and weaker in other directions. Every time those electrons accelerate, they're sending out light of their own, not just absorbing the incoming wave. Of course, in real materials, there aren't just one or two dipoles, there are billions. In this animation, you're looking at a whole column of dipoles inside the material. They're all being driven by the same incoming light wave, so they oscillate in sync. Each one is re-radiating light forwards and backwards like a perfectly choreographed line of tiny antennae. It's the combined effect of all these dipoles that creates the delay we measure as refractive index. This next animation makes the delay clearer. The blue dashed line is the original incoming wave, and the orange dashed line is the wave emitted by the dipoles. Notice how the orange waves lag slightly behind the blue ones. That's because the electrons take a fraction of a cycle to respond. The key takeaway? That little delay shifts the wave's overall phase, and over many cycles it adds up to the light appearing slower in the material. Finally, this animation shows the process across the entire wavefront. Each point in the material acts like its own little source of light, radiating waves that interfere and combine to form a new wavefront. This constant handoff, original wave to dipole, dipole back to wave, happens trillions of times per second. When you zoom out, all you see is the light traveling at a slower speed, but close up, it is this beautiful, coordinated dance of wavelets. Now, not all radiated light goes forward. You might have noticed some of it goes backwards or off to the side. If we add arrows to our columns of dipoles, you can see light being scattered in random directions. If you take a look at the image shown on your screen, you can see light being scattered in random directions. This is called Rayleigh scattering. Even in the purest glass, this scattering causes tiny loss, about 0.14 to 0.15 decibels per kilometer in optical fiber. Over an undersea cable, that adds up, which is why we need repeaters to boost the signal. There's one more twist. Refractive index changes with wavelength, a phenomenon called dispersion. Electrons in atoms act like they're attached to springs, each with its own natural vibration frequency. The light's frequency is close to the natural resonance, the electrons move more, which increases the delay. Different colors of light have different frequencies, so they travel at slightly different speeds, and that's why a prism can split white light into a rainbow. So that's refractive index, not just a number in a textbook, but a microscopic relay race between light and electrons. We've seen it step by step. How the electric field moves electrons, how those electrons act like antennae, how billions of them combine to create a delay, and how that delay gives us refractive index. If you've enjoyed this deep dive, subscribe. I post new videos every few weeks exploring the physics of light and photonics. Thank you for watching.